This polar nature of the molecule that allows for hydrogen bonding explains pretty much every special property that water has for life, including how this water strider can be standing on top of the water. Last time you tried to stand on water, you probably did a worse job. And the sad truth is, if I were to tap this water strider on the head and push some of his legs through the surface, he would also not do very well. He would drown. So he exists constantly on the surface of the water, close to his death, but never reaching it. All thanks to what exactly? If you look very closely, that is, you would need a finer microscope than any we have invented so far, at what's going on here near his legs, here's what you'd see. If you picture the leg kind of like this, then right under it the water molecules are cohering to each other. That is, they're hydrogen bonding and forming a net that holds the water strider up. When water hydrogen bonds with itself and forms this surface tension across the top of the water, scientists call that cohesion. And this same cohesion is even allowing this snail here to crawl along the bottom of the surface of the water and scoot out across a lake. In plants, cohesion and its sister property, adhesion, are very important for transporting water from roots up through stems and to leaves. In this diagram you can see water getting taken up by roots and then slowly transporting itself upward. But what's actually transporting the water? There's no pump. The tree isn't doing huge amounts of work. How is it that the water just moves upward? It's almost like magic. Again, water's polarity explains. The tissue that the water travels up is called the xylem, which you can see right here, and it forms these tubes through which the water moves in an upward direction. And it does so by adhesion and cohesion. First off, you already know what cohesion is because we just talked about it. You can see these two water molecules have a hydrogen bond running right through the middle of them, where one water molecule pulls on the next one, pulling it upwards towards the top of the tree. Then there's also adhesion to the inner walls of the xylem. That means that the walls, just like the glass in the previous picture, have some charges, and the water molecules are attaching to those charges, and that's what allows the water to climb upward. So if you pictured the inside of the xylem tissue, there might be, say, a positive charge right here, and maybe a negative charge right here, and just the occasional charge is enough for the water to adhere its way up, with the positive hydrogen end of the water molecule attracting to negative charges, and the negative oxygen end attracting to positive charges. And while adhesion is the steam engine, cohesion is the links between each car and the train, and up goes this long train of water molecules, one after the next, all the way until they get to the leaves, where they can be used for photosynthesis. Hydrogen bonding also explains why sweating cools down our bodies. Let's say we're generating all of this heat from, I don't know, say we're exercising. Right, so there's all this heat. And heat, by definition, is the movement of molecules. So that means that in the surface of our skin, our molecules are moving all around because of this high temperature. And as our molecules move all around, they give a little kick to water molecules from time to time. Kick, kick, kick. Normally, when a liquid receives enough kicks, its water molecules start changing state and floating away in the form of gas. Now, this is true of water too. The difference is, though, that before this water molecule can break away from the droplet, a hydrogen bond needs to be broken. That means that the water droplet can take heat and more 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 heat until those water molecules are moving so much that finally this water molecule will be like, I can't take it anymore, and off it will go to evaporate. So the fact that the hydrogen bonds are holding the water molecules together, helping them cohere on our skin, means that that droplet of sweat can take more and more and more energy just to get rid of that small amount of water, which makes the water in the sweat a very effective cooling mechanism. The polarity of water not only explains the transition of water from liquid to gas, but it also explains stuff about the solid state of water, specifically that of ice. You will notice, for example, that these penguins are making good use of this huge iceberg right here, which they can do only because the ice is floating, otherwise it would make a pretty terrible resting place. The fact that ice floats is actually a pretty rare phenomenon in the universe. Most of the time, solids are more dense than liquids. That means their molecules are more closely packed together, which means that they weigh more. So if you took some solid steel and you dropped it into a pot of molten steel, then that chunk of solid steel would sink right to the bottom immediately. But water, solid water, floats on liquid water. How could that be? Hydrogen bonding explains it again. So let's pretend that you're a water molecule, and you're really part of the liquid water. You haven't yet become part of the ice, but you're about to. So if you're in a liquid state, you're moving around and you're moving around, but you're starting to get a little bit slower because the temperature is dropping until suddenly you're so still that bam! You can hydrogen bond with the nearest water molecule inside the ice. That hydrogen bond holds you at a very specific distance from the last molecule and in a specific shape. And as water molecules join in this geometric pattern, they're held apart so that they make a very spacious crystal. And when I say spacious, I mean it. Look at all of this empty space in here. Holy crap, there's so much empty space. Contrast that within liquid water, where all of the molecules are packed super tight and you can hardly find any space between them. This is why ice floats on water. Further evidence of this geometric hydrogen bonding in ice comes in the exquisite shapes of snowflakes, as depicted here. Now, ice makes humans grumpy sometimes, particularly because it often results in car accidents. So we take some molecular strategies for stopping this hydrogen bonding from occurring. When we add salt to sidewalks, we use adhesion to break up cohesion. You guys already know that ionic compounds such as this salt crystal right here contain charged particles such as chloride ions that are negatively charged and sodium ions that are positively charged. Well, when water comes in contact with that, the water molecules adhere to these charged particles, as you can see in this diagram. The positively charged sodium attracts the negatively charged oxygen ends of the water molecules, whereas the negatively charged chlorine attracts the positively charged hydrogen ends of the water molecules. When the water molecules are busy attracting to new particles, it's harder for them to attract to each other. So while these free water molecules might be able to hydrogen bond okay and form that nice complex ice structure, the ones that are over here interacting with these ions are not able to. And so the presence of ions disrupts the ability of the water crystal to form in that complex geometric pattern, and thus we stop ice from freezing on our roads when we put salt on it. A final characteristic of water that makes it essential to life is its ability to shift from being more acidic to more basic, or to stay right in the middle. Organisms are made of very complex molecules such as this receptor protein right here, and the molecules will easily lose their shape if they're not surrounded by the right kind of chemicals. This protein specifically exists on the outside of our blood cells, and in our bodies, blood is kept at a pH of 7. At any other pH, this protein will cease to function, so it's critical that our bodies maintain the appropriate pH in the appropriate areas of our body. A pH of 7 is considered neutral and was originally based on pure water. What that means is if we had a really fine microscope where we could look at the atoms and molecules inside the water solution, this hydrogen ion floating around every 10 million water molecules. Hydrogen ions are pretty rare generally, particularly in pure water. And this protein is used to no more than 1 in every 10 million. I'm getting that statistic, by the way, from this area of the pH scale where it says 10 to the negative 7th. pH actually means the power to which the hydrogen concentration is raised. That's a complex way of saying 1 in every 10 million water molecules, you'll get a hydrogen proton mixed in there as well. Anyway, technicalities aside, most of our body, and indeed our blood, is kept at this neutral pH of 7. What happens if pH gets out of balance? Well, this protein here is held in this complex shape thanks to some very special bonding that's happening within the molecule. And its bonding you already know. Take, for example, this positively charged hydrogen, which is being attracted to this negatively charged oxygen, and it's forming a hydrogen bond, and that's holding part of the protein together. Down here, you've got an ionic bond with this NH3 positive ion and this O part of a negative ion. Well, these ionic bonds and hydrogen bonds can hold the protein in this complex shape just fine until the pH gets out of whack. Let's say the pH gets really low. Let's say it becomes very acidic. That means that H plus becomes a lot more common. Now imagine if there was a whole bunch of H plus particles hanging out. That would spell bad news for this protein, because, say, this positively charged ion would be repelled away from that positively charged ion, this negative ion would be attracted to that positively charged ion, and the same thing over here. You get some repulsion and some attraction, until the protein could no longer hold on to itself, and it would instead become this long, unwound shape, rather than this carefully wound and bundled functional protein. The moral of this story is hydrogen bonding is important to our bodies in many, many ways, and when acids or bases become involved, sometimes that can fiddle with the way an organism normally hydrogen bonds, often for the worse. So the special properties of water all revolve around the fact that the oxygen atom has that extra pull on electrons, which means the electrons hang out down here, which means one end of the molecule is negative and the other end is positive. This allows it to hydrogen bond, to cohere, to adhere, to make ice less dense than water, and to make water an effective cooling mechanism during sweating. Salts and acids can interfere with this hydrogen bonding and thus alter the way that water and the organisms that contain it normally behave. Behaviors that are dictated by the atoms and the subatomic particles within it.